In this lecture, we're going to be finishing our discussion on basic concepts of thermodynamics by talking about pressure. First of all, what is pressure? Well, by definition, pressure is what we're going to be considering as a normal force, and the units of this force are per unit area. So basically, it's a force per unit area. And here's a good illustration showing somebody who is 150 pounds, which I'm not, and somebody who is 300 pounds, which I'm closer to, having the same foot area, basically the same person. If they gain that weight, the pressure on their feet will be much greater when they weigh more than when they weighed less. Some typical conversions are here too. You'll see that 1 bar is 100,000 pascals or 0.1 megapascals. We will be using and considering 1 atmosphere in our calculations, typically at sea level, which is 101,325 pascals, or 101.325 kilopascals. That's something we'll be using quite a bit together. And of course that varies. Here in El Paso, the atmospheric pressure is quite a bit lower than it would be at sea level. But regardless, we'll consider sea level as our reference point. Now, how do we quantify pressure? There's 3 different considerations we'll be making when we talk about pressure, but really we're only going to be talking about the first 2, absolute pressure and gauge pressure. Absolute pressure is measured relative to vacuum. So pretty much always, if you're on Earth, you're going to have an absolute pressure. If you go to space, you will be pretty close to or at vacuum. So when there is nothing present, and we can simulate that type of environment by pumping out air out of a certain chamber or out of a certain controlled experiment, but typically we are going to have a pressure reading. We refer to pressure in the atmosphere that we feel pressing down on us as atmospheric pressure. Above atmospheric pressure, we will have a gauge pressure. So atmospheric pressure is 0. Gauge pressure is 0 when reading an atmospheric pressure. Here you'll see the conversions between them. And you can look at those and study those carefully. But this is what I want to emphasize here to help you kind of to remember what gauge pressure is. So you look at these gauges here in the lower left-hand corner. Well, the gauge, and you'll see that all these gauges are open to atmosphere in this picture. They're all reading 0, and they're open to atmosphere. Now we know that the absolute pressure around us is not 0. The absolute pressure around us is about 101,325 pascals. But when we read it off a gauge, it says 0. So anything above 101,325 will register on our pressure gauge. Now, if we're talking about a fluid, and here looks like we have some type of water. It's blue. I'll say that it's water. How does pressure vary as we go underwater? Well, pressure varies linearly as we go underwater. At the top, we'll have atmospheric pressure, and as we go below, we'll add a factor, and this factor is the density of the fluid we are using times gravity times the height that we are at. And as the H increases, we'll see a linear increase of pressure down to the floor of this pool. Another thing that's interesting about the variation of pressure is that if we go in the x direction, So let me get my mouse over here. In the x direction, which means left to right, if we look at the pressure at a particular location here, we'll see that the pressure is the same on all locations that are horizontal. So pressure remains the same at a given depth. It doesn't vary in the horizontal direction. It varies in the vertical direction. And it varies linearly. So let's take a look at it. Does it depend now on the geometry? So let's say this was a really bumpy bottom here. Well, let's look at that. At points A, B, C, D, E, F, and G here, they're all at the same horizontal level. And even though they are around different geometries, the pressure is equal at all of those points. Now, if we go deeper, we know that pressure increases linearly with height. So the point I will have a higher pressure than all the others that I just mentioned. Something else to note is if we have a different fluid, the pressure will be higher. So here we have H that is in mercury. H will have a higher pressure than I, because H is subjected to more weight pressing down on it. Now, we've talked about fluids. What happens when we have a gas? So looking at an air in a room, air is going to be heavier at the bottom of the room. And here you can see a calculation of a 15 meter high room or a 5 meter high room. At the bottom, if we consider the top at 1 atmosphere, we would have 1.006 atmospheres at the bottom. Do we need to take this into account? Probably not. It will simplify our calculations greatly to assume that pressure is uniform throughout this room, and we'll be doing that when we deal with gases. Now, how do we take advantage of this pressure that we can measure? One of the tools that we use to measure pressure and to take advantage of this effect of pressure variation with depth or with more weight is the manometer. We can use the manometer to measure flow, so in an open system, or we can use a manometer to measure pressure in a closed system. So in the top example, we have fluid flow. That fluid flow causes a pressure difference between points 1 and 2. Well, we can measure that pressure difference if we put a manometer between the two. We will come back to how we measure the pressure difference between 2 points of manometer during our problem-solving session in the next lecture. But in general, you can see that as we have a higher pressure, for example, in this tank, the manometer height will increase. So basically, this pressure in this tank will push this fluid, whatever it may be, higher in this column. That change in height we can relate to a pressure through this equation. And we'll work several of those examples. Another practical application that you may hear all the time is the use of a barometer. A lot of weathermen use the barometer to describe the weather. Now, a barometer measures atmospheric pressure. Basically, we have atmospheric pressure pushing down on this liquid, which is then recorded or seen and observed through the rise of fluid height in this tube. Typically, what you'll see is that if you have a high pressure or pressure is high, this fluid goes higher in this tube, weather will be clear. Lower pressure, or the fluid decreases in this tube, may be a rainy day. And weathermen typically use trends that they observe to describe the weather. So as the manometer reading or the barometer reading falls, that typically means a storm is approaching. A rising manometer may mean that it's sunny. Or if it's very low, it may mean that there's a strong storm coming. One last example to talk about pressure is its effect on machines and even our human body. At high altitudes, there's less pressure and less oxygen because density is lower at high altitudes. When there's less oxygen, car engines may generate less power. And in some cases, our bodies can be seen as an engine. We take in fuel and then we produce CO2. As we burn our fuel, one of the products is CO2. So maybe we perform worse also in lower density air. A lot of times you may see Denver Broncos people go play at the Denver Broncos Stadium, Mile High Stadium, and they may be sucking air, breathing harder because of the less air that is available at that place. So we've completed now our discussions on temperature and pressure and some basic concepts in thermodynamics and some basic nomenclature. What I'd like to do now is I'd like to work some problems together so that we can practice and apply some of the things that we've learned with some problems.